And if it is okay with you, Ramandeep, we will start.
Sure.
So hello, everybody. Thank you very much for joining us today for this online virtual seminar of the Institute of Astrophysics. It is great to see all of you. We have the great pleasure to have with us today Ramandeep Gill from the Instituto de Radioastronomía y Astrofísica of the Universidad Nacional Autónoma de México. Ramandeep obtained his bachelor's degree, but also his PhD from the University of British Columbia. And then he moved on to postdoctoral positions in Theta, at the Goethe University, the Open University of Israel, the George Washington University, before moving to the Instituto de Radioastronomía and Astrofísica, where he is today. We are very excited to hear today his talk about ultra-relativistic jets in gamma-ray bursts. And since I have also been just talking today in my astrophysics graduate class about relativistic jets, it is a great companion for the students as well. So thank you very much, Ramandeep. It's a great pleasure to have you, and the floor is yours.
Great. Thank you so much for the introduction. And I'll say hello to everyone who's tuned in today for this talk. So let me start by sharing my screen. Okay, I hope you can see, sorry.
Yes, we can see.
You can see my presentation screen. So as you just heard, I'll be talking about ultra-relativistic jets in gamma-ray bursts, and in particular, I'll be discussing their angular structure. So before I go on, I would like to acknowledge some of my collaborators who've given their time and expertise to some of the work that I'll be showing you results from. And I understand you've had a talk recently about GRBs, so you're all well primed up for the introductory thing that I'm going to mention in the next few slides. And of course, I'm sure Nikos must have been telling you all about GRBs. So this might come as a review to you. But what are GRBs? GRBs are bright cosmic beacons. They are one of the brightest high-energy transients that we have in our universe. And so basically, as the name suggests, they emit these bursts of gamma rays over a short duration of time. And this initial bright phase, which is also referred to as a prompt phase, is so intense that looking at the gamma ray sky in this picture, it can actually overshine the entire gamma ray sky. So this is, as you can see, it is a very brief sort of event. Otherwise, the energetics would be huge if it lasted over a much longer time. But over this brief event, it emits an impressive amount of luminosity. So just a second, let me close these windows coming into my way. So over this very brief duration, it displays a very impressive luminosity. So this is the isotropic equivalent luminosities gathered by the Fermi GBM catalog gamma ray burst monitor. And you can see that the luminosity can be anywhere on the order of 10 to the 52 ergs per second to 10 to the 54 ergs per second. And given their brief duration, the corresponding energies, isotropic equivalent, are on the order of typically 10 to the 52 ergs to 10 to the 54 ergs. Now, because they are so intrinsically bright, they are seen at very large distances. So this is the distribution of GRBs as a function of redshift that we've seen so far, mostly by the Swift Space Telescope. And you can see that we've seen GRBs all the way up to a redshift of 9.4. Now, this very quality makes GRBs an impressive and very useful probe of things like star formation. Okay, or if you want to study the extragalactic background light, where these gamma ray photons that the GRBs emit interact with cosmic ray background photons, or UV and infrared light coming from the stars in the universe. And also, it is a very interesting probe if you want to learn something fundamental, do some fundamental physics, and learn about the quantum structure of our universe, because at small scales, it could be Lorentz invariance violation. So GRBs act as useful probes to sort of track these interesting effects. So you see there are different, there are long and short GRBs mentioned on this slide. So what are these? Well, when we look at the duration distribution of the prompt phase emission of these GRBs, we find that there's a bimodality. Okay, and the dividing line between the two distributions sits around 2 to 3 seconds. It is an instrument-dependent dividing line, but typically it's around 2 seconds. And the GRBs sitting in this branch here are classified aptly as long GRBs, and the GRBs sitting here are short GRBs. This is not the only difference that you find between the long and the short. When you look at the hardness ratio or the peak energy distribution of these two clumps, you find that there is again a bimodality. Okay, so the red blob here, these are the long GRBs. They tend to be spectrally softer in their peak energies, and the short GRBs, the blue clump, tend to be spectrally harder. So, for example, the red clump, the mean sort of the distribution might be sitting around 200 keVs or so, and for the blue clump, the mean is much higher, maybe around 800 keVs or even an MeV. Okay, so they're much harder. And we have come to the realization that some of these effects, especially the time distribution, is due to the kind of progenitors these populations have. Okay, so now we know that the long GRBs are the progeny of massive Wolf-Rayet stars. So these massive stars undergo core collapse. Okay, and they produce a compact remnant which launches these jets and produce the GRBs. And we have, we don't have a direct evidence, but we have indirect evidence in terms of the kind of supernovae that are associated to these events. They're called the broadline type 1c supernovae, which have the telltale signatures of not having any helium or hydrogen envelopes in these stars, and that shows that these GRBs must be coming from these Wolf-Rayet stars. Okay. On the other hand, the short GRBs, the population is associated with the merger of compact binaries, either neutron star mergers or neutron star black hole mergers. And now we do have direct evidence for these, but for a long time before that actually happened, we had again indirect evidence in terms of which part of the galaxy, what type of galaxies these are associated with, and that tend to be always elliptical galaxies, and they're always offset objects from the center of the galaxy. So we had indirect evidence for these, and again, these two objects, the compact objects, merge, form a compact remnant which launches these jets. So the end product in both of these scenarios is the same. So in both cases, you have a compact object. Most likely it is a black hole, although you can find a lot of literature on this where people do believe that it could be a rapidly spinning, strongly magnetized neutron star, or referred to as a millisecond magnetar, which could also launch these relativistic outflows. And so what happens when an outflow is launched, either by this black hole or a magnetar, it starts to interact with the ISM. But before it does so, very far away from the central engine, at a distances of around 10 to the 11, 10 to the 12 centimeters, it undergoes this internal dissipation, some kind of internal dissipation, which we're not really clear about. But one of the popular sort of mechanism is having this central engine eject these shells, the mass shells, which interact with each other and then shock heat the plasma, which then emits these gamma ray photons that we see as the prompt emission. And this relativistic ejecta continues to expand and interacts with the surrounding ISM or the wind environment, if it was a massive star, and then gets slowed down and shock heats the material that it collects, and that emits synchrotron radiation, a broadband radiation, which is emitted over these broadband of energies, all the way from radio, visible, X-rays, and gamma rays, which we see as the afterglow from these sources. So just, if you're not dealing with, ultra-relativistic sources, just to give you an idea that the jets from these sources are traveling upwards of bulk Lorentz factors of 100. What does that mean? In terms of the velocity in units of speed of light, it is going practically at the speed of light, 0.99995. Okay, so these objects are moving very fast, which is one of the draws and one of the interesting things that at least for me that I was drawn to study. So okay, so this is what we actually see. Okay, this is the entire picture. So this is a very well sampled GRB, GRB 190114C, and it is an impressive GRB for various reasons. One is of course the broadband coverage it has, and also this was the very first GRB that showed TV emission, which is shown by these green dots here. Okay, so let me try to present some distinguishing features between the prompt phase and the afterglow. So the prompt phase, as I mentioned earlier, is the short-lived phase, okay, anywhere between 10 to the minus 1 seconds or 100 seconds, and it is highly variable. So this is the emission that you would see, and you see a lot of these oscillations going on with very short variability timescales. And it is very different from what you see, what happens later on. So the prompt emission is just the tip of the iceberg. A lot of additional information is presented when you look at the afterglows. So this is what represents this long tail of emission that represents the afterglows. As I mentioned earlier, it is purely synchrotron emission for most part, but this magic emission that we saw, it is not synchrotron, it is most likely synchrotron self-Compton emission, okay? Although it is not quite clear, there are various other hadronic and other leptonic emission models that could explain this, but most likely it is believed to be XSC. So what you see here is broadband emission over all these different energy bands and well sampled here. And it is lasting much longer than in contrast to the prompt emission over time periods of days, weeks, and even months. And the interesting thing that you compare between the two, the prompt and the afterglow, is that how temporally smooth it is. So if you look at delta T over T is already unity, okay? The time scale over which the emission varies. And we very well understand where this emission is coming from. We know how relativistic blast waves, when they interact with the surrounding medium, what is their, if the medium has this profile where it goes out of the minus K. Do notice of this this power law index K. It will come in many of my slides. So keep in mind, this is what I'm referring to when I mentioned this, this index K. And we fully understand how the Lorentz factor scales as a function of radius when these blast waves are being slowed down by collecting a lot of this circumbrist medium. And we know that's from Blanford-McKee for a long time, since we see these things happening not only in GRBs, but other events such as AGNs, okay? So this is all very well understood. All the physics here is very well understood, and we're able to understand the different characteristics of this emission. But what we don't know so far is what is the angular structure of these GRB jets. So this is practically the outline of my talk. And the goal here is for me is to try to answer some of these questions, or to provide tools or mention ways in which we can use to constrain the angular structure. So what we want to know here is what is the actual angular structure? What is its origin? How is this angular structure produced in these jets? Is it different in long and short GRBs? How different, and what might be the cause of those differences? And what can we use to probe these differences and constrain the properties of the flow? So you might be wondering, well, can we use the prompt emission to probe the jet angular structure? And the quick and short answer is you can, yes, but it is quite challenging. And the reason for that is quite simple. Because these flows are going at such high relativistic speeds, the emission from them due to the aberration of light effect is very much beamed in the forward direction. So you can only see a very small part of the flow, okay, from which the emission is coming from. So I'm trying to demonstrate that here in this cartoonish picture here, where you have a flow, okay, going at such high Lorentz factors. You can only get emission or information from an angular region of size 1 over gamma, gamma being the bulk Lorentz factor of the flow. Okay, so you're limited to probing only that part of the flow, which is quite tiny because, as I mentioned, gamma is very large, upwards of 100. So this angular size of this emission region is quite small. So for example, if you have a much bigger flow, if this is the angular size or the aperture of the flow which is emitting the radiation, you are only privy to this much information here, okay, during the prompt emission phase. But what happens when you get the afterglow is that the jet slows down, so this ratio becomes larger, and then you can see much larger portion of the flow. So you have much more information. You are able to sort of scan the angular structure of the jet. So this is what you need. You need afterglow emission, which has much more information than the prompt. But that's not to say that you cannot understand the angular structure from the prompt emission. You can, and there is a tool which is linear polarization, very impressive tool to use to understand. And I will not go into too many details here because that deserves a talk on its own. But I'll just give you a very brief example. So this is the polarization that you see as a function of the viewing angle, which is theta observed, or the inclination angle measured with respect to the jet symmetry axis, divided by the core angle of the jet. Okay. So basically this aperture size that you see here, this is, for example, let's say this is theta core. So within, so this is as a function of that. And you can see for different parameters, and in the next few slides, you'll understand what these A's and B's mean. So for a jet with some angular structure, you're able to distinguish between different angular structures, given this polarization that arises from the photospheric emission. That is when the jet becomes optically thin and releases the thermal radiation. So there are ways that you can use the prompt emission, but more information can be understood from the afterglows. Okay. So this, the outflows in GRBs should be jetted outflows, which it was understood much earlier in the late 90s by Rhodes and papers by Ray Sari, where they envisioned that a lot of energy is being released and that it must be channeled into this jetted outflow. So that sort of gave birth to the idea of a very simple and idealized model called the top hat jet model, in which the emissivity or the energy per unit solid angle and also the Lorentz factor of the flow is like a top hat, basically. So the distribution of that on a log-log plot would look like this, where it would be uniform and then cut off where you hit the edge of the jet. That is the size of your cone. Okay. And it would look similar to this. So imagine yourself as an observer, and then you're looking at some GRB, and this is your viewing angle. So these people, when they talked about this, they also envisioned that if this is what's really happening, then at some point when the beaming cone of this becomes wide enough so that you start seeing the edge of the jet, okay, which is here, then the emission or the light curve should show a steepening. Okay, so that's what's referred to as a jet break, where the emission would steepen by, for example, a power of 1 in time. So going from t to the -1, the light curve would go as t to the -2. Okay, and the interesting thing about this is that it is a geometric effect. Okay, it doesn't have to do anything with the spectrum of the emission. So since it's a geometric effect, it should affect all the different wave bands. So if you're observing in optical X-ray, gamma rays, whichever, you should see this steepening happening in the light curve. So which means that the steepening is achromatic. And this basically comes from the fact that, this is sort of the definition of when this should occur, is the beaming cone, which is the angular size of which is 1 over gamma, becomes large enough so that you're able to get information from the edge of the jet. Okay. So this was recognized much earlier on. And then we've, over the years, over a few decades, we've had sources that do show this steepening, this jet break clearly. And this is a nice example. It is shown over all these different wave bands, and you see a clear steepening happening. So this was observed for many such GRBs, and there's a distribution here shown, which allowed us to sort of constrain the opening angle of these jets. Okay, so this is what theta jet means, and typically the angle is around 5 degrees or so. So which means, because these are jetted outflows, the energies that I mentioned at the very beginning of the talk, those are isotropic equivalent energies. The true energies are much smaller, precisely by this beaming factor f sub b, which is basically the ratio of the opening angle, the solid angle of the jet, divided by 4 pi. Okay. And this is typically, given this distribution, is typically on the order of 10 to the -3. So you reduce the energy budget that I mentioned earlier by factors of 3 orders or 4 orders of magnitude. Okay. So now what you notice here, that the true energy is a combination of this f sub b factor and also the isotropic equivalent energy that you actually measure. And you can see from this plot, there is a lot of variation happening here. There's a lot of dispersion in these two parameters. So the people try to come up with a universal structure model where they envision that let's say that you have a single kind of GRB jet with a single energy budget, and all of these variations that you see in the isotropic equivalent energy are simply a variations of the viewing angle that you have. So they made attempts to sort of unify the structure, something very similar to what happened in the field of AGMs, where you see different type of objects, given your inclination angle. Okay, so that sort of, I mean, it had that sort of modeling didn't pan out so well. It had some weaknesses, but it gave birth to the idea of thinking of these jets in terms of angular structured jets, having this sort of a, one of the popular models that was put forth is that of a power law jet, where rather than having a top hat, which I showed you earlier on this log-log plot, the emissivity or energy per unit solid angle and the Lorentz factor gamma as a function looks like a broken power law, where you have a relativistic core up to an angle theta core, and then it declines in energy and also in bulk gamma as a power law. Okay, so the sort of the physical picture to have in mind is that you have this relativistic core surrounded by weakly energetic, slowly moving material like a cocoon or a cloud. Okay? And then, this is basically sort of mathematically shown here how things would scale as a function of theta, where theta is the function of the smaller theta, which is measured from the jet symmetry axis. All right. And this is what the A and the B, as I mentioned on the couple of slides back, these are the power law indices for this structure that I was referring to. And you'll see more of these in the next few slides. So this is one popular model. The other model that you might see mentioned a lot in the literature is called the Gaussian jet, where you have a similar type of structure, but now the wings are dropping in energy and bulk Lorentz factor much more sharply as an exponential. Okay, so this is very much close to a modified version, basically, of a top hat jet, but the edges of the jet are now much more smoother. Okay, rather than being sharp. So these are the two popular models that are always considered now, and they're quite general in terms of given these power law indices A and B, you can sort of generalize these profiles and use these then to fit to observations. Okay. All right. So let me spend just one slide discussing what is the origin of these. Okay, these are sort of phenomenological things that we've discussed with which to sort of characterize the overall angular structure, but what is giving rise to those things? Okay, so keep in mind that in order to emit the gamma rays, the relativistic jet has to bore its way out of the confining medium. So it is never a sort of a naked environment in which the black hole is sitting, without any surrounding medium and then spitting out these jets. There is always a confining medium, and that is purely because, for example, in the case of short GRBs, as these two objects merge, coalesce, they eject a lot of material, and as they form an accretion disk, there's always this disk-driven winds that is ejecting a lot of material in the path of the jet. So the environment is always sort of filled with material through which the jet has to bore its way out. So for the short GRBs, it turns out it has to be the dynamical ejecta, which is sort of a homologously expanding cloud. And the fastest, the outer edge of which goes, it's subrelativistic, but it goes at fairly high speed, the 0.2 to 0.3 C. That's for the short GRBs. When we turn to the long GRBs, well, naturally we have a star through which the jet has to propagate out. Okay, so that becomes the confining medium, and compared to the short GRB, in the case of long GRBs, it is much more dense. So that sort of instills some differences that you might see in the angular structure. So what happens when you introduce a jet into both of these confining mediums? The physics that occurs is pretty much the same, but there are differences because as I mentioned, for the long GRB case, the densities are quite high. But this is a basic picture, a cartoonish picture that I'm trying to show you what happens when you introduce a jet. Well, in most simulation that you find, people are introducing conical flows. These are relativistically hot flows. Typically introduced at Lorentz factors of gamma 5 or 10 or so. But as the jet tries to propagate through the confining medium, the head of the jet slows down considerably because it has to plow through these layers of stuff, and it shock heats. So it forms this two-shock structure, okay, which is shown here and much more closely in here, where you have a forward shock which propagates ahead of this contact discontinuity, and it heats up the confining medium, okay, the gas in the confining medium, and there's a reverse shock which propagates backwards into the jet and shock heats the jet itself. all right? And then at some point, because the jet is coming very fast from below, this material is moving much more slowly. It is able to move sideways or expand laterally away from the head of the jet and starts pouring onto the side and forms these inner and outer cocoons, where the inner cocoon is the shock-heated jet material and the outer cocoon is the shock-heated confining medium gas, okay? And these are pressurized cocoons. So what they do, they start applying pressure to the head of the jet. And then the jet then reacts to it by going through this intricate sort of compression, rarefaction compression, because of these collimation shocks due to the pressure applied by these cocoons. And you see these sort of physics taking place in both cases. Here I'm showing you one of the hydrodynamic simulations where the jet is trying to propagate out of the star. This is an example where the relativistic jet has broken out of the confining medium in the case of short GRBs. Okay, so what you see here is you see a lot more collimation shocks happening in this picture, not so much, but it is still there. All right, so the physics is still very similar, but there is one striking difference, and that is you see a lot of mixing happening when the jet is propagating inside a star, because first of all it is spending a lot more time, and because the star is much more dense, it is susceptible, this contact discontinuity which forms between the two cocoons, it is susceptible to relative instabilities. And the more mixing that occurs, the more it affects the final outcome of the structure. So the mixing happens in both cases. It happens much more in the long GRB case compared to the short GRBs. Right? So when we look at the final structures, so this is sort of the thing that we find. So in our recent work, what we've done is we've curated some of the results from simulations that were conducted by, in this work, Gottlieb 2021, and also by Davide Lazzati in 2017. And what we've done here is we have used our phenomenological, these profiles that I showed you earlier, fit to the results of the simulation. So the dashed lines that you see here show the angular structure, the energy, the isotropic equivalent energy as a function of angle that we find from simulations for both the short GRBs and the long GRBs. And we've done the same thing to fit this profile for gamma to the velocity gamma beta, the proper velocity profile in these two simulations. And what we find here is they're very, both of these are quite similar. There are some common general features which I point out here. One is, of course, there's always a uniform core. Okay, you see that here in both cases. There is some, uniform core in energy. Okay, and also in the Lorentz factor profile. And then after this core, it drops off almost like a parallel. Okay, in both of these cases. Okay, and then at some point it dropped exponentially. All right. So basically, in the central part where you see this uniform structure, this is the relativistic core of the jet. This parallel wing is due to the mixing that happens between the cocoon shock-heated material and the shock-heated jet material, and that gives rise to this parallel wing. And then here, this is the basically the cocoon, this pressurized cocoon that expands out of the confining medium, and that's its energy profile and velocity profile. Okay, so both of these things are quite common in long and short GRBs. Again, the striking difference here you find is that in the case of long GRBs, due to this extra mixing, you find that this A parameter is rather shallow, small, compared to having a steeper profile for the short GRB case because the mixing is quite less. There are also interesting differences when you look at magnetized jets. Okay, in these cases, what you find as the magnetization, which is defined here, basically the enthalpy density in the magnetic field. Okay, there's a co-moving quantity shown with prime. So d squared over 4 pi is the enthalpy density in the magnetic field, divided by the enthalpy density of matter, shown as the specific enthalpy density times rho t squared. So that sort of quantifies, if the jet is strongly magnified or weakly magnetized. And these are one of the example simulations that as you crank up the magnetization, you start to see changes in the angular distribution of the energy and also the velocity profile of these jets. It tends to become much more steeper. These profiles become much more steeper. And the reason for that is because you have now magnetic fields, you are kind of suppressing that relative instability that was happening. Because of that suppression, there's not a lot of mixing going on, and that's what gives you these sharper profiles. Okay. So in a way, if you're able to constrain the angular structure from observations, you can actually get to the heart of the problem in GRB physics is what is the composition, and from what I mean is what is the actual magnetization of the flow, which we have no clue. Okay. So that's one of the central questions that everybody's trying to solve in this field. So there could be different simulations sometimes lead to slightly different results. This is simulation that was done in my work by Antonius Nathanael, which shows again this is a GRMHD simulations. So what you find here is something interesting going on. So one thing to point out, these jets in this simulation are expanding inside a star. In this case, we're simulating short GRB jets, so they're expanding inside a much less dense confining medium. And what you find here is this, you may find this hollow cone. So this is showing you the Lorentz factor. So that's what this color means. And what you see here is there is material that is moving very much slowly, and there is some offset material in this blob, which is moving much faster than material along the jet axis. So you do find some of these peculiarities when you do these simulations, and they are important when you're trying to understand the afterglow of these sources. And then again, in both cases, you find steeply falling profiles, as well, of course, for the short GRB scenario, as you mentioned, you get these steep profiles, and because in both cases you have magnetized jets, that also sort of enhances the steepness of the angular profiles that you see. All right, so that's all the sort of theoretical modeling of the structure that we expect to get in long and short GRBs, and whether they're weakly or strongly magnetized. But what do you expect from the emission, the afterglow emission that these jets emit? Okay, so let me start very briefly from the idealized and simple model to give you some understanding of what goes on. And it boils down to the idea that if you do want to understand the angular structure of these flows, you must be looking at the jet at an angle. So the jet must be misaligned or off axis, because if you're looking on axis, okay, meaning looking down the barrel of the jet, it is very hard to get any information of the angular structure. And this is the reason why we haven't been able to sort of constrain the angular structure, because most of the GRBs that we see, first of all, they're very distant sources, and there is an observational bias, because most of the energy, since it is clustered around in this core here, and we only tend to see the GRBs that are pointed towards us, and our line of sight is actually cutting across, okay, close to the jet symmetry axis, meaning that we're always on axis. So we needed an event, a nearby event, where the jet can be misaligned and off axis. Otherwise, the emission will be too dim and we can't really see. Okay, but that's actually what we need. So when we are misaligned with respect to the jet axis, what happens? So in the case of a top hat jet, okay, the initial emission is beamed away from us because the jet is relativistic. As it slows down, this beaming cone widens, and then we start getting emission from this, the closer edge of the jet. Okay, and it looks like this. So this would be the afterglow that a misaligned observer at different misalignment angles would see. So an on-axis observer would see this, okay, a declining afterglow. So there's the flux density going as a function of time. So this is the light curve, afterglow light curve an on-axis observer would see. But as you become more and more misaligned, you notice two things happening. First, well, three things rather. You see this very sharply rising emission, okay? And for any given sensitivity, what you will notice is that the emission would start at a later time compared to what an on-axis observer would have seen. Okay, and that becomes, the time over which you see becomes longer and longer. The larger is your viewing angle. So, for example, if your theta observed or your inclination angle is as large as your theta naught, or your opening angle of the jet, basically you're grazing the edge. Or if it's twice as that, 3 times, 5 times, so on and so forth. But what you also notice is that the peak of the emission, where the peak occurs, is much more suppressed now. Okay. And had you been an on-axis observer, you would have seen at an earlier time much brighter afterglow emission, which doesn't happen for an off-axis observer. Okay, so that's what sort of the challenges that come in when you're looking at distant sources, that they become much more fainter. Now, this is for a top hat jet. We've been discussing jets with the angular structure. So what do you get in that? So this would be the light curves, okay? Similar picture would be the light curves that you would get from some of the short GRB angular profiles, that I showed on the previous slides. This is for different viewing angles that you would see. Now, notice there are some similarities, but there are also very interesting difference, and that difference is this. So notice here there is a very striking peak. Now that peak in this case, when you're an off-axis observer, becomes almost like a shallow rise to the peak. Okay, and this is due to the fact that there is more energy that is slowly added to the line of sight of the observer as more and more material, which is sitting closer to the jet axis, comes into view as the jet slows down. All right. So let me explain what I mean by that. So here, going back to the profiles that I've been discussing. So this is the energy per unit solid angle as a function of angle measured from the jet symmetry axis. And I'm showing you two different profiles. In the red, there is the Gaussian profile, a Gaussian jet. In the blue, and the solid lines I'm referring to are the energy per unit solid angle. The dotted lines show the angular structure in terms of the velocity or proper velocity, gamma beta. So blue line is parallel jets and red lines are Gaussian jets. And imagine that you're an observer looking at this flow at an angle of, let's say, 25 degrees, okay? So then, because of the beaming effect, because of the aberration of light, you can only get at any given time information from angles. This is angle from which light is coming to you, okay, as a function of time. The smallest angle from which you can get emission is shown here. And because of this widening of the beaming cone as time progresses, you see emission coming from smaller and smaller angle, getting closer to the jet symmetry axis, okay, until you reach the core of the jet. All right. So this is basically coming from the equation that I showed you earlier, which ties it down to the dynamics of the flow, which is affected by the angular profile or energy profile. So that's why this parallel index A shows up here, and also the radial density profile of your confining medium or external medium into which the jet is propagated. So all of these things sort of conspire to give you this sort of curve, which shows you over time the angles from which the emission is becoming unbeamed towards you. So perhaps this slide will make much more sense in terms of it'll shed more light on what I'm trying to get across here. Is that here's an example of a light curve that you might see, and pardon me, and just to give you an idea of where the emission is coming from with respect to your inclination angle, and pardon me, and with respect to the jet axis, I'm showing you this flux density as a function of solid angle. Okay, so this is basically a map as a function of time. So what you see, the contours are this df nu d omega. So basically what it means is that if you were to add up, integrate over all the solid angle at any given time, you would make a flux point on this light curve. All right. So at the initial time, at earlier times when you're in this rising phase, the emission is coming just along your line of sight. Okay, you're dominated by material that is sitting along your line of sight. But as the time progresses, these contours which show where the dominant flux is coming from which angles, they move from your viewing angle towards the jet axis, okay, which is shown here by the white cross. And slowly over time, most of the emission goes closer and closer to the jet axis, and that's what gives you this rising profile until you hit you see the core of the jet, and after that, since you've now seen all of the jet, the emission declines. Okay, so this is basically this part is basically what you would expect from a spherical flow. All right, from a spherical flow, you don't see this rising phase; you simply see this declining part. All right. Now this is happening for if the angular structure is sufficiently steep, and this is the kind of light curve that you expect. But there are different variations that are possible, and this is what we something that we try to point out in this detailed work, which basically sums up all the different ways of different kinds of light curves that are possible for a given set of parameters in terms of the angular structure and so on that you have for the flow. So I showed you on the previous slide this type of light curve, but another variation is this. This is also possible. So the difference is you see one peak, but now you actually see two peaks. And that sort of boils down to the fact is what, compared to this special angle, what's called theta star, what is your viewing angle, okay? So theta star is a special angle in the sense that any material sitting at angles smaller than this theta star, it is strongly beamed, okay? Any material that is sitting above this angle is not so strongly beamed. So that's where all these two differences in the light curves come through. So if I can spend maybe a minute discussing this, although it's quite a technical picture here. So for example, let's focus on this scenario where your viewing angle is smaller than this theta star. So what happens is, as time progresses, material at all these different angles in the flow is decelerating, meaning that initially it was moving at a constant bulk Lorentz factor, and then it starts to decelerate because it is collecting more and more of the external medium and slowing down. And at some point, so this dashed line shows all the angles as a function of your observer time when they decelerate. So if you're sitting at this theta observed A, you hit, you're initially looking at emission coming from along your line of sight, which is theta observed A, and then it decelerates, okay, at this time, and that's when you see this peak. And after this peak, you see this phase which you would have seen even for a spherically expanding blast wave. And the reason for that is the emission from all the other angles is strongly beamed away, and it takes time for that emission to come into view. Until you hit this, this blue line, that's when it actually happens. You start seeing this rising phase of the emission, which is because there's more energy sitting at smaller angles, which is now coming into view. And that is being added to your line of sight, increasing the flux density as a function of time. And then as time progresses, you see the core of the jet, which is the second peak, and then again a decline, okay? Something that didn't happen here, which was the scenario of B, where you don't have this complicated thing happening and you go all the way, and you see all of the emission, it is completely unbeamed. So when your flow decelerates along your line of sight, which happens here, you are able to see all the emission from smaller angles. And then again, the same picture continues, the same scenario where you see the core of the jet and then it declines. So now we understand, so all this how the angular structure affects your light curve. That's not the only thing that the angular structure affects when you are a misaligned observer. It also affects some of the critical frequencies of synchrotron emission that you see. So in general, when you're looking at synchrotron emission, the afterglow, you see this sort of spectrum, which is a broken parallel spectrum, and it is sort of characterized by these three different frequencies. If your electrons are cooling fast, meaning they're rapidly cooling, as long as, as soon as they're accelerated, they emit all the energy right away. They're in the fast cooling regime. If they're not, if the cooling time is much longer than the dynamical time, they're in the slow cooling regime. So, mostly when we talk about afterglows, we're in the slow cooling regime, and this is the kind of spectrum we see. And we, for all the on-axis GRBs, we understand the temporal evolution of these critical frequencies, okay? But when you have a misaligned flow, this temporal evolution, which was rather, just a straight parallel, very much straightforward, becomes very much complicated and adds more detail due to the structure that we have. I won't go into, this is a very complicated picture. I won't go into the different phases, and only point out that when you're looking at an on-axis GRB, with which you cannot probe the angular structure, you're only seeing this part of the temporal evolution of the critical frequencies, for example, nu C as a function of time, or this part when you're looking at nu M, one of the break frequencies as a function of time. All of these other things you cannot see, but more information becomes available when you're a misaligned observer, okay? So it leads to all this complicated evolution of the critical frequencies. Other things that I will briefly point out that you can track how the structure affects the light curve, in a very interesting way. For example, if you set K, which is the radial density profile of your ISM, if you set that to 0, meaning constant ISM, And if you crank up the steepness of your structure, it brings up interesting changes. For example, going from this purple line to this yellow, where your energy structure is becoming much steeper, you start seeing this second peak develop, okay, which wasn't there before. So this is some of the changes that occurs to the light curve, which you can use to constrain the structure of the jet. But it turns out that it is degenerate with changes in the value of K. For example, if you fix the value of A, and if you crank up the this K parameter, then you can again produce similar things that you saw in this picture. So it leads to some degeneracy, but if you have additional information, you can actually constrain independently this parameter A and this parameter K. Okay, so it can give you some insight about the density distribution in the circumburst matter into which the jet is expanding. So all of this stuff that I said earlier, that is for a very steep jet. Okay, something very interesting and remarkable happens when the angular structure is not as steep but rather shallow. So what I mean by that is that there is a critical A. Now this is the power law index for the energy profile, energy per unit solid angle as a function of angle that I mentioned. And there is a critical A if the actual A of the jet, the profile of the jet is smaller than this critical A, then that's what we refer to in our work as shallow jets. And the most interesting thing that happens is the emission, the angle that dominates the flux density as a function of time. I showed you for steep jets, it always goes towards the jet symmetry axis, which would be this red case. So over time, that angles become smaller, 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 starting from your observing, your inclination angle. It goes towards the core angle, okay, or the jet symmetry axis. But that is true only for steep jets. But if your jet happens to be in the shallow regime, you see this very opposite trend where this theta F, which dominates the emission, becomes larger and larger. Okay, so I'm trying to show that in a more sort of understandable way here. The bottom part is the picture that you saw earlier, where these contours starting from your viewing angle move towards the jet symmetry axis over time. Okay, but the opposite trend occurs in the shallow case, where A is smaller than some critical A. These contours, okay, move to larger and larger angles. Okay, meaning the emission is coming from the jet is not steep enough to give you emission from smaller angles. Rather, the solid angle of the flow starts to dominate the total emission, which is coming from much larger regions around your line of sight, and that causes this rise in the angle that contributes most of the emission. Okay, so this is something very interesting. And one can go ahead and do the same exercise in terms of tracking the behavior of those break frequencies that I mentioned as a function of time. Okay, so one thing that I failed to mention earlier is that the evolution of the break frequencies in the steeper jet case did not depend on the angular structure. For example, did not depend on the power law index A in the previous case. So although that makes it much more robust in the earlier case, but you cannot sort of constrain this parameter A for a steep jet. But when you have a shallow jet case, you actually can, given this trend. Okay, so that's something interesting that you see in a shallow jet. And okay, something I'm quite excited about. Very interesting happens due to this behavior. The switching between steep and shallow is the fact that this critical A depends on sort of the energy at which you're looking at, whether you're looking at in the optical or in the X-rays. So, for example, let's say you're looking in the optical, which would be this red line that I'm trying to show here. That would be the light curve, and if you're looking at in the X-rays, that would be the blue one. And now the idea is this, and I mentioned to you early in the talk, these jet breaks. These jet breaks not only occurs in sharply edged jet, but also in these angular structured jets. So compared to a spherical flow shown here by this dotted line, where you don't expect any jet breaks, but just to give you an idea how much of a suppression in flux that you see in the two cases, what you see here is that the suppression in flux, okay, after the flow suffers a jet break, is not the same. okay? Meaning it is not achromatic. So what we've done here is, due to this, this acritical parameter, we've introduced chromaticity into the suppression, which is quite interesting. So, here is another example by how much this suppression occurs. It is not as huge in the red case, but much larger in the blue case, where red would be the optical emission and blue, for example, would be the X-rays. And that's something that we haven't seen so far, because we've never had so many cases of off-axis GRBs. So since they're very hard to see. But let's say in the future we do see such cases, then we can constrain the angular structure quite precisely, given that we see these chromatic behavior. I will point out one thing, that we do see chromatic behavior in the regular GRBs that are seen on axis, and this is shown here in this some compilation of different GRBs where you see a break in the X-rays, but not so much in the optical. And we don't, I mean, this is still a big puzzle that people are trying to solve. We don't know what might be causing this. Perhaps it is something similar to this, where the break in the optical is rather smooth and not as sharp as you see in the X-rays. Perhaps if that's what's happening. So that remains still to be tested. But it is an interesting prospect that you get from having this angular structure in your jets. Okay, so I think I have a very little amount of time left. Just to confirm, how much time do I have left? If anybody can confirm.
Maybe 5 minutes.
5 minutes. Okay. So we've discussed, in the 2/3 of this talk, all the theoretical sort of modeling that we've done, and how we can use that to constrain the jet angular structure. But what about the actual observation? Do we have such a scenario which that we've used to constrain the angular structure? And a golden opportunity presented itself in the form of this GRB, which was the biggest sort of thing that happened, at least in my career studying GRBs, is this merger of two neutron stars from which we detected the gravitational waves, and coincidentally, at the same time, we detected prompt from GRBs from the source, and that's shown here by the detection by Fermi and integral in gamma rays, and also the gravitational wave chirp signal. So this was sort of a big event in many things. First opportunity to have a direct sort of observational evidence that a merger of two neutron stars, which was theorized long ago, can actually produce gamma ray bursts. So this was a smoking gun, but many other interesting things came out of this. For example, there was a certain delay between the chirp signal and when we actually see the prompt emission, and the delay was precisely 1.74 seconds, which has very interesting implications about the remnant that was produced and how long it survived until it collapsed to the black hole and launched the jet. So the longer it took for it to collapse, that added to this delay of 1.74 seconds. So one could say something interesting about that. And also, it takes time for the jet to propagate out of the confining medium. So how long did that take? That sort of tells you something about the properties of the jet itself, and also the properties of this expanding cloud of debris through which the jet has to propagate. So many interesting things came out of this event. But it was a very peculiar, in terms of its prompt emission properties and in terms of its afterglow, it was quite peculiar, something that we hadn't seen before. Okay, so in terms, when looking at the prompt emission, the energy that was emitted, it was, very much smaller compared to what we see in other standard short GRBs. So this is sort of a distribution that Fermi has put together. So the yellow dots would be these. So now these are intrinsic. This is an intrinsic property, the energy that you see from other sources, and these are much larger compared to what we saw in this scenario. Okay, when it comes to the prompt emission, and also the afterglow. It started very much late. So now, you can relate back to what I said earlier, that when you have misaligned jets, the afterglow emission starts late. And this is precisely what's happening here. So these are the radio observations, and it shows a late rise to the peak of the afterglow. So both of these sort of, these evidences gave good indications towards that indeed in this event, we have a misaligned or off-axis jet and the observer is indeed off-axis. And also the fact that we don't have, in this case, a top hat jet, but instead we have a jet with some angular structure, and we're seeing emission, especially the prompt emission, which was subluminous compared to the other cases. We're seeing emission coming from material that is sitting along our line of sight. If it was a top hat jet, there wouldn't be any material, but in this case, there is a material that is emitting the GRB photons along our line of sight. Okay, so we already had some idea that this is sort of the kind of scenario we're dealing with, and then people try to try the basic simple model, which is again the top hat jet, to gain an understanding in such a case where you can explain the observations or not, the afterglow observations, the light curve with a initially top hat jet, and it failed. It didn't work because you couldn't explain the shallow rise to the peak. Okay, you would always see this steep structure. We made several attempts in terms of try to sort of do more detailed modeling by carrying out some hydrodynamic simulations. Again, we were able to only explain part of the rise, but not all the shallow rise to the peak that we saw. There would always be this steep structure. So basically, top hat jet model was out. It could not explain the afterglow observations, and it had to be the emission had to be coming from a jet with some angular structure. So a lot of people, at that time, carried out similar modeling in terms of explaining the afterglow light curve that we saw in different energy bands, and try to explain this shallow rise to the peak. So this is an example from my work where I'm using again the Gaussian jet and the parallel jet, trying to constrain these A and B parameters. And other shock microphysical and energetics of the flow, and this is we made synthetic images of what the jet would look like as it for an off-axis or misaligned observer. Basically, before it is convolved with your detector response function. This is something that one would see if one could resolve the GRB, and so this is what you would see for a Gaussian jet and a parallel jet. The reason why you see this additional blob is the counterjet. It's the emission from the counterjet that is becoming visible to you at much later times. Okay, so one of the predictions that we were able to make while carrying out this exercise is that if you have a jetted structure like these, a Gaussian or a parallel, you should be able to find a large offset in the angle that is producing the most of the flux. Okay, so the flux centroid basically should show an offset from the position of the GRB, all right, as a function of time. And then people did VLBI radio observations, and this is what they found. So they measured the position of this flux centroid at some time and at some later time, and over this duration of several days, they found an offset of 2.7. And if I go back, now this work was done before this measurement was done. If I go back and put those lines, where the measurements were made, we were in the ballpark. So the idea being that when you have jetted structures, which people, there was some confusion about, whether you have a jet in this case or whether you have just quasi-spherical cocoon expanding. So we made the prediction that if you have a jetted structure, you expect a large motion of your flux centroid, and indeed that was the case. So this is, when we had more data over time, we were able to do a much better job in terms of constraining the models that I showed you earlier. These are the profiles that I showed you earlier for the short GRB jets coming from the hydrodynamic simulations. And they do a very nice job in explaining not just the early time, but also the late time data as well. Similar efforts were done using these detailed hydrodynamic simulation models. Different groups have produced that. And the interesting thing that happens is at late times, these models are good enough that they can constrain the viewing angle and also the core angle of the jet. Okay, so they become discerning enough at late times that you can actually rule out some of these models. Right. And finally, just to sort of wrap up, one of the, this is going back to the discussion that we were having earlier before the start of the talk, which is polarization. And polarization is a very useful tool to understand and constrain the angular structure of the flow. But there's always a problem that linear polarization is degenerate in when you have angular structure. Basically, it depends on both the anisotropy of the magnetic field, which is emitting the synchrotron photons behind your forward shock, okay? And also it depends on the angular structure. So you have to sort of constrain one of them using independent measurements, other diagnostics, and those are the light curves that we saw. So what we've done here is by fitting to the light curves, we have constrained the angular structure. So we've removed the degeneracy that sort of crops into these polarization measurements out. So now everything sort of solely depends on the anisotropy of the magnetic field. And so in this work, what we're trying to do here is for this GW 170817 event, we're trying to predict what is the anisotropy of the magnetic field just behind the forward shock. Okay, so the reason why we're doing this is because from theory and from also particle in cell simulations, the prediction is that the magnetic field that produces the afterglow lies completely in a plane transverse to your shock normal, or basically transverse to your local velocity vector. Okay, meaning that is highly anisotropic. So what we've done is we've characterized quite generally the anisotropy of the magnetic field. Basically the ratio of the magnetic field along the local velocity vector divided by the magnetic field strength perpendicular to that. So this gives you the level of anisotropy of the field and how it actually sort of changes as a function of the similarity variable as the fluids that are shocked at the shock front and travel back into the flow. And we've carried out this exercise to produce for different anisotropy parameter just behind the shock, which I'm denoting psi f, and for different values of anisotropy parameters, we get these polarization curves as a function of time. Okay. And what we've done here is we've used the constraints provided by the radio observation for this GW 170817 event. There was not a measurement, but just an upper limit. And what it does is it constrains the level of this psi f. And that is what's important when comparing with these trick simulations or the theoretical modeling that has been done in the past. And what we find here is that since the theory predicts that psi f should be much, much smaller than 1, but the observations constrained by, the models constrained by these observations are telling us that psi f should be closer to 1. Psi f being closer to 1 means that the magnetic field behind the shock is rather more isotropic rather than being more anisotropic, which the theory predicts. So it really refutes or challenges basically the idea that shocks that are produced in the afterglows perhaps are not Weibull generated entirely, but there's some other mechanism that's going on, which is isotropizing the angular structure of the magnetic field. Okay, so this is some very interesting thing that comes out from modeling, doing the angular structure modeling using the afterglow, and also looking at this polarization constraint. Okay, so let me conclude by saying that numerical simulations show clearly that GRBs jets have angular structure. They are not top-hat jets, although top-hat jets are a good sort of pedagogical tool to sort of understand the basic properties. But in the end, if you want to be more realistic and accurate, you need to have angular structure in your model. Of course, whenever you're looking at misaligned jets, it becomes quite important to have that feature. And this is also one of the important lessons we learned from GW 170817, because we did have access to emission coming from larger angles from the jet symmetry axis, which allowed us to constrain that angular structure. And what we need at this point to sort of go forward, a lot of work has been done over the past few years where people have carried out MHD and hydrodynamic simulations. We need more of those. We need more systematic studies in order to characterize, because in all of these studies, people pick different parameters. So we need a systematic way in which to, and there are, of course, different knobs that people can turn. So we need a systematic study to sort of bring out, what are the universal sort of structure and features that we find in, jets that are propagating out of a star in long GRB cases, or jets that are propagating out of this debris in the case of short GRBs. And what I've shown you over the past few slides is that one can do these semi-analytic modeling, which becomes a powerful tool to not only verify your numerical results, okay, which is quite useful to have such a tool handy where you want to verify your numerical results, but also it's quite powerful in fitting to observations and constraining the angular structure of these jets. And finally, the most important point that I want to get across is that the central open question in GRB physics is constraining the magnetization of the flow. Are they strongly magnetized flows or are they weakly magnetized flows? And given that strong magnetized jets have this very steep energy and bulk Lorentz factor structures compared to their weakly magnetized counterparts, if one is able to, with future events, can constrain those, that can really nail down and solve many of the open questions that we have regarding to the prompt emission and also regarding to the overall properties of the jet in GRBs. I'll stop here. Thank you so much.
Thank you very much, Ramandeep. That was extremely interesting and very, very relevant to what we're doing here. So thank you for this great talk. Any quick questions, anybody? You can either raise your hand or just open your mic and ask. Nico, go ahead.
Thank you, Ramandeep. Very, very interesting. And I was also very excited when you showed this gravitational wave detection together with the GRB. I was just wondering, you showed the top hat jet and a couple of other models. And I mean, you conclude that jets do have angular structures for your simulations. But is one observation enough to rule out the top hat model, for example? And like in a more general way, do you expect all jets to have a similar structure? Do you exclude some of them to be top hat and some of them to have angular structure, for example? Thanks.
So let me make the distinction, when top hat is not useful or when it is useful. So for all the, all the 99% of the GRBs that we see, top hat is perfectly fine. The reason why that is because we only see a part of the jet, okay, which, and we don't have additional information given the observations, given the light curve and the spectrum that we see. We don't have enough information to distinguish it being from not a top hat jet, okay? So for 99% of the GRBs, top hat is perfectly fine, but that's not the true story. That's, and we only get access to what the actual structure is by having these misaligned jets. And that would happen in GGW 17.17. So let me quickly try to answer your question. I guess you were referring to these modelings where people couldn't explain using a top hat jet, okay? So that really, and the reason why, because this shallow rise to the peak was created precisely by the jet having this angular structure, which the top hat doesn't have, right? So what we're trying to answer is, what is the true structure of the jet that is produced, okay? And it is not top hat. It does have some angular structure. The question remains how steep or shallow that structure is, how steep or shallow those wings are. Okay, so that is sort of the next step, what we want to constrain. Does that answer your question, Nikos?
Yes. So you basically need more events like that. You need to be a bit...
Absolutely. So we've been, I mean, this was very lucky that we were able to catch this, but, we're hoping to catch more of these in the future. And, such events are, in the literature referred to as orphan afterglows. And we have seen some orphan afterglows where we don't see the prompt emission because it is beamed very much away from your line of sight, but because the afterglow is much more isotropically emitted at later time as the jet expands, you're able to catch the afterglow emission at least, okay? And we have some of those events, but it's not as good as the 170870, because I mean this event was only 40 megaparsecs. So we got extremely lucky in many respects when we had this.
Thank you.
Any other questions?
I have another one if there's nobody else.
Go ahead, Niva. I have a question too, but please go ahead.
Yeah, I mean, I don't know if it is a short answer or another talk, but you said something in the very beginning, in the first slide, that you can probe star formation with GRBs. This is something I've never heard. I mean, if the answer is short, could you say a few things? Or...
Yeah, the short answer is, well, all of these, I mean, they're coming from stars. So what you're doing is you're tracing, looking at their luminosity function and folding that into how it changes over redshift. You're tracing, these are products of stars. So they are sort of indirect, signatures of star formation, right? So these are coming from massive stars. They only live for tens or so millions of years, these massive Wolf-Rayet stars. So, and then they produce the GRB there. And then you're basically tracking the amount of these massive stars that you see as a function of redshift. So it is a tracer or a probe of star formation, over cosmological time.
Okay, I get the point. Yeah, makes sense. Thanks.
Yeah.
Anything else for Ramandeep? Okay, so let me ask my question then, while other people are thinking. So my question is, especially for short gamma ray bursts, now that we have established that, at least some of the short gamma ray bursts come from neutron star mergers, right?
Right.
So when it comes to neutron star mergers, the thing about them is that fundamentally they are all very similar to each other, right? There is not that much variation between different neutron stars. And this is why, for example, it was argued in the long ago, before we had the stars, that the R process happens in this kind of mergers, that this is a likely environment just because the ratio of R process element abundances were so stable, right? So they had to be very similar event to event. So I'm trying to think, other than viewing angle and I guess environment, is there anything else that would cause fundamental physical variations in the GRB quantities, for example, total energy released or things like that, in short gamma ray bursts, assuming that a large majority of them comes from these types of mergers? Or do we actually expect most of the variation in the observable properties to come from variations in the viewing angle and their environment?
Right, that's a good question, and actually we're on the right slide to sort of answer that question. So you see here for the short GRBs, it's a very sparse sample, but you get some idea of that they are not all emitting the same type of level of energy. So there is some spread here, okay? And pretty much all of these that are shown here were observed on axis because they are distant, redshift 0.1 or beyond sources. So there is no way that we saw these at off axis. So off axis sort of question aside, looking at just even the on axis ones, there is a whole variety of spread in energies and also the spread in luminosities, these purple things that you see that this is all referring to the prompt emission. And the reason why that spread is there is because even though the merger physics is similar, going back to what you asked, you don't expect a whole lot of variety in terms of the energetics that you have in these sources. The problem is we can't really answer this question why there is such a large variety of E-isos, the isotropic energy that we actually measure. And that goes back to the point that we don't really know how this energy is being emitted. We don't really know the exact mechanism that produces the prompt GRB. So this is, again, the prompt GRB energetics. So, and that again goes back to the crux of the point, the conclusion that I was trying to get across is that magnetization is so important, and the composition of this jet is so important that we have no clue about. We have models that talk about weakly magnetized flows, which are basically fireballs, right? The fireball model, it has its own sort of assumption that it is its own results. And then we have sort of more strongly pointing flux dominated flows in which, you have, rather than this internal dissipation, you can have magnetic dissipation. We have all these different ideas to explain some features, some the spectrum and other things, but that's, we don't have a clear picture yet of why do we see this spread. So even though the basic underlying energetic, the collision, the merger physics is the same throughout all the different mergers, we don't have a clue why do we get a spread in the total energetics that we actually measure.
Okay, great. That's very, very interesting. Thank you.
Sure.
Any other questions for Ramandeep? Okay, if not, and since it is getting late, let me thank you once again very, very much for this great talk. I will stop the recording now.